very much to the organizers and to the Institute for having me the last couple of weeks. I really had a lot of fun. So today, what I want to do is attempt to sketch a path by which we can start from qubits and get all the way to Einstein's equations. And because of time and because of the fact that there are technical details that still haven't been worked out, this is not a complete program yet. But I will hope to show you that it's plausible, that the concepts are basically in place, and to give you a few concrete results that are really important along the way. Okay, so that's what I want to do today. So what's the motivation? Well, we have gravity, right? In the real world, things fall down. and more than that, this gravity is actually quantum mechanical. It seems. It didn't have to be so, perhaps, but it seems to be true. The most basic argument for this fact starts with the ultraviolet catastrophe and electromagnetism, which people dealt with at the beginning of the last century, in which you said, okay, I have electromagnetic waves, they have some equilibrium distribution, but that equilibrium distribution has a divergent energy. Right, but then if I put Planck's constant in there, then that regulates that divergence, and I get something finite. And so, in fact, people had measured Planck's constant in a sense. They had measured what's called the Stefan-Boltzmann constant, which was essentially Planck's constant. You know, in the previous century, in the 19th century, it was already known. But there's no really crucial conceptual difference between electromagnetic waves and gravitational waves. So a similar argument would suggest that gravitational waves, which we know exist, at least indirectly, also can feel h-bar. Maybe more direct recent evidence would be, for example, this recent fantastic measurement from Bicep 2 that you may have heard about, where they have observed in the sky angular fluctuations, which are, your thumb is like about a degree, the moon is half a degree, so they see multiple degree fluctuations in the sky, which are supposed to be primordial quantum gravitational fluctuations that have been amplified by inflation. So it's really the same that you can see in a few degrees in the sky, you can see the effects of quantum gravity. That's one of the implications of the most direct reading of the recent experiments at Bicep 2. So really, quantum gravity is a real thing. It's not just a theorist's toy. It exists in nature. We'd like to understand it. And so for my purposes, what that means is I'd like to have a Hilbert space and a Hamiltonian. So I want to have kinematics and dynamics, right? And it may be that quantum gravity has some aspects of quantum mechanics and not others, so maybe this is not the right ultimate goal, but let's try this goal and see how far we can get. And then once I give you the Hilbert space, a very important step will be to recover semi-classical physics.
Excuse me.
Yeah.
Do you impose this dual product structure, tensor product structure in the Hilbert space?
I will, yes.
So that's as one input.
Yes. But the Hilbert space will not be a local Hilbert space in the same dimension in which the gravity lives in the semi-classical limit. So there will be something special. You'll see.
But it does have this tensor.
It does have a tensor product structure. Yeah. How this tensor product structure corresponds with bulk locality in the semi-classical limit is not necessarily obvious. Okay. So this is what I want to do. And I think the goal is indeed to tell you what this Hilbert space is, to tell you what the Hamiltonian is, and then to show you a plausible route to getting the semi-classical physics out. And let me give you a few clues, since this is a tensor network workshop and not a quantum gravity workshop. Let me give you some clues as to what quantum gravity should look like. The first clue is the Hamiltonian is a boundary term. This is because, in electromagnetism, I have a charge. I have some charge in a region. I can measure that charge at infinity by looking with little test charges, right? So I can measure the total charge enclosed in some large system. But in gravity, the charge is mass itself, right? So I can measure the total mass of a system by looking at infinity at the effects of little test particles moving in essentially the Newtonian gravitational field of that total mass. But because mass is itself energy, then this means the Hamiltonian is itself observable from infinity. So the Hamiltonian is really a property of the asymptotics of this space in some precise sense.
Universe, energy equal to 0.
Yes, so I'm really thinking in this case about Minkowski space, but for a closed universe, yeah, something like the energy is 0 basically. Just in the same sense that you can have no net charge in a closed space, right? Field lines have to end somewhere. So that's one clue. The second comes from black holes. Very famously, black holes can be associated in entropy, which behaves very much like thermodynamic entropy. And this entropy is related to a geometrical property of the black hole, which is the area of the event horizon, in some units, which we call Planck units. So this is Newton's constant. And there's various h bars and c's that have been put to 1. Okay. So this told us the Hamiltonian was really some kind of boundary term. This suggests that the Hilbert space has a very peculiar structure when gravity gets strong. That the degrees of freedom don't live in volume, they live on surfaces, which is again similar to what we saw in the Hamiltonian case. And the third clue is what I'll call, well, let's just say it's gravitational redshift. Which says the following. If I had a star here of some mass m, and I started out with a little atom here, which emits a photon to infinity, so this is r, and this is r equals infinity, then the frequency that I would observe at infinity is the frequency that I would produce at r times a factor, which is interpretable as a gravitational redshift. That is, the photon has to climb out of the gravitational well, and so it loses some energy. Right? And so in this sense, going back to this point 1, if I look at infinity, at energy, then the energy of a photon deep inside the bulk, when viewed at infinity, is very low. Right? So somehow going inside the bulk, away from the boundary, means going to low energies.
This is already first electromagnetic, right?
Sorry?
You already take a space.
Yeah, this is a spherically symmetric star of some mass m. So this just follows from the Schwarzschild geometry. And in fact, if you expand this out, you'll see that it's omega r 1 minus gm over rc squared. This is the Newtonian potential. So it's just saying that I have my original mass minus the gravitational energy, and that's equal to the energy at infinity. Okay. So these are the clues, and the buzzword that goes with these clues is to say that gravity is holographic. Quantum gravity is holographic.
Why is this related to the
Well, this is really a statement about the first two, but the third is a clue about what the radial direction means. Is that it's associated with different energies. The same excitation, the same photon emitted at different places corresponds to different boundary energies. So the first two say that the metric, the Hamiltonian and the Hilbert space are somehow area things. And the last one tells you how to interpret the radial direction as energy scale in the boundary. Okay. So,
Excuse me, here's
Yeah.
one thing is that for the black hole,
yes.
I think the last point is very interesting. But usually when you have a black hole, when around black hole is not ADS metric, right? So
No, that's right.
That picture is like if you go into the ADS metric direction, then you go to 100. But the black hole is have different metrics. So
Yes.
whether this can be a problem or
Well, no. So it's a good question, and the real issue is how to interpret. Let's say, in this black hole, conventional black hole, the asymptotics are not ADS asymptotics; they're Minkowski asymptotics. So things look different. The asymptotics are null instead of time-like.
yeah.
So this is maybe, let's just say it's a motivation at this point, and then in the ADS case, it will become quite precise.
I see.
Okay. Right? So what I want to do is, so what this tells you is that whatever quantum gravity is, it depends sensitively on the boundary conditions. So I'm going to consider a particular kind of boundary condition where the boundary is time-like, which roughly means that time survives at the edge. So it's not like the space at infinite future or some kind of null light-like thing. So I can write a metric, which looks like this. So this r is called the ADS radius. I introduce some coordinates, r, t, and x, which may be a vector. And the picture is like this. I have x, I have r, and t comes out of the board. And the boundary, r equals 0 is the boundary. And this is the bulk. And this is the kind of space that I'm going to ultimately, this is just a preview basically at this point. This is the kind of space I'm going to address, where time survives at the edge. And quantum gravity is easiest in this case precisely for that reason, that time survives at the edge. So I have to do less work. Instead of having to produce both time and space, I only have to produce space, which is a simpler task. And although this toy model is not describing our universe as far as we know, quantum gravity is a sufficiently complicated beast that it makes sense to understand this toy model completely and then see if we can move on to some other kind of asymptotics. Okay. So what I'd like to do is
There's also, you have dt squared, have a coefficient 1 squared. That's a,
yeah.
if time is, I wonder, should you take dt squared out? So time is totally,
No, you shouldn't.
I see.
And this is related to this point,
I see.
that time runs slower the farther down you go. So this is precisely this gravitational redshift. So I'm going to start in the middle, which is to tell you an intermediate point, which we'll kind of take a break at in the path from qubits to Einstein's equations. And that is going to involve entanglement in some way. So that's the key ingredient here. So the start in the middle is I'm going to assume that I have some CFT. And why is it a CFT? Because the symmetries of the CFT are realized as isometries of this metric. So for example, the scaling symmetry, where x goes to lambda x and t goes to lambda t, are implemented with r goes to lambda r. And that's an isometry of this metric. Okay, so that's why the CFT enters the story.
But doesn't that mean you have no massive particles? Or you just ignoring them?
Well, in the CFT, I can create excited states of some energy, but yes, all the elementary excitations, if you like, are massless in the CFT. But that's different. In the bulk, they'll be massive. Okay, so I have a CFT, and the claim is that the Hilbert space of the CFT equals the Hilbert space of quantum gravity. This is Maldaceno's claim, also called ADS-CFT. And I have various properties. I'm going to assume that I have a smooth, semi-classical geometry. And I have some entanglement structure, which I'll specify in a minute. And the basic correspondence is that I have some state of the CFT, and it's just literally equivalent to some data in the bulk, which will be some geometry G, which is the metric, and some state of bulk fields. And these bulk fields include things like the graviton. If you have a conserved current in the CFT, it would include a gauge field in the bulk. It can include other kinds of fields. And to compute entanglement in these states, what I do is I do the famous Ryuta-Kinagi formula, or really just this black hole formula again. So it looks like this. So A is a region in the boundary. A tilde is a minimal surface with respect to G, this metric in the bulk, and sigma is the interior. And again, this is all at fixed time. And the fundamental assumption will be that the entanglement entropy of A in the CFT state is equal to the area of A tilde this minimal surface in this geometry in some units, plus an extra term, which is the entanglement entropy of the bulk degrees of freedom in their bulk state. Right. So this is what I'm going to assume. Okay. For the second part of the talk, I'll assume this. And so the structure is going to be, I'm going to start from qubits. Let's call this star. I'm going to go to star. And then I'm going to go to Einstein. This is the path. And to go from qubits to star, I'm going to use tensor networks. And to go from here, I'm going to use geometry and quantum field theory in curved space. Okay. And this part is done with Mark van Ramsdonk. Okay, that's the plan. And so this is kind of the fulcrum on which the whole argument is going to hinge. So first I want to make this plausible using tensor networks. And then I want to use this to get Einstein's equation.
So what is this assumption? Can you explain? So A is a segment on the...
Yeah, so let's, and drawing in one dimension, so A is an interval,
I see.
right? And I say that the entanglement entropy of the A in the Cft state, so this is just Cft side, can be evaluated on the gravity side by looking at this minimal surface, calculating its area with some prefactor, and then computing the entanglement entropy of the bulk fields. So this is my assumption. Yeah?
So you're working in a Schwarzschild kind of geometry? Or?
No, so I'm really working with this ADS geometry here.
But X is the orthogonal to the radius. Right?
Yes, X is like the field theory direction, and then R is down. Yeah.
Do you only consider the ground state of the CFT, or also?
Well, so I'm assuming this formula is true for all states, or for some class of states, let's say, some class of semi-classical states.
Stationary states, or also?
No, they could be time dependent. But I'll mostly what I'll use my argument is only the ground state and small perturbations from the ground state. That's all I'll really use. But in principle, I think I could assume that what I want to do is assume this is true for some class of semi-classical states.
So usually people don't have a second term, just a
Yeah.
entropy just equal to the area.
This will be important.
Okay. So
Very
the
important.
second term is subleading or have
Yes.
the same order contribution?
It's subleading. If you think of G Newton as being very small, so that you have sort of semi-classical.
I mean, subleading, is that still area? I mean, imagine the second term also area law. So
Well, it
also-
could be area, but it could also have like long-range pieces, long-range entanglement,
Yeah.
right? So like this could be a topological state, so it has an extra minus log 2 or something.
But from scaling point of view, it can contribute to the mix with the first term, which also scale as area of the...
Yeah, in principle it could mix. So this is an important issue about how to regulate this thing in the bulk, because this area contribution typically is associated with UV physics. So there's a sense in which we can take this area piece and move it over here, and that defines the low energy Newton's constant in some renormalized theory. So there's a whole story told most recently by Cooperman and Ludi, which talks about how to think about renormalizing this in terms of some effective gravitational piece. But I won't actually evaluate this. I'll only evaluate changes in it.
But can one say that so maybe the second term is only topological entropy? Well,
Yeah, I think
that's
roughly you should think of this term, and that's, and when I derive this later, it'll just be some kind of really global stuff. It's just some global entanglement.
the local things. Of
Like if I put a a qubit here and a qubit there, then it would be log 2. They were in some singlet. Yeah.
So is the Newton-Takayanagi formula applicable to time-dependent geometry?
Well, there's a generalization which says I should find some extremal surface, right? And that formula is not necessarily known to be correct. But here I won't. I'll just apply it to stationary solutions and small deformations thereof. So it's, I think, okay in that case. It's just my assumption. I'm not actually deriving this. You can derive it, but I'm just assuming it, or I will derive it from some different way. Yeah.
How do I think of side load as a matter, or?
Yeah, so it includes the graviton at least, because you have some geometry. But yeah, if you have some scalar fields or whatever in the bulk, it's just those matter degrees of freedom. Sorry? Yes, yes. Okay. So let me do part 1. Which is qubits to star. Okay. So for part 1, okay, I start with qubits. Here are my qubits. Okay. Let's arrange them in a one-dimensional line, and they have some local Hamiltonian, H local. But I want to be in a special case. I don't just want to treat general situation because I don't expect that I have semi-classical physics in the most general possible case. I want to be in some special limit where gravity looks semi-classical. And so that limit is where the easiest thing to do is where this is at a critical point. So I have some kind of scale invariance. I have a CFT, in fact. And the local dimension is large in some parameter. So let's say in each site there are many qubits. And I arrange them in this one-dimensional line, and these many qubits interact strongly in some unspecified way. But so the total Hamiltonian, which is local, is a critical Hamiltonian. And the fact that it's critical and it's a CFT suggests that we take this RG perspective. And so what we want to do is use Mira. So I'm not going to justify this any more than to say it's sort of a reasonable thing to do. You can justify it better, but that's previous talks I've given. So in order to get to Einstein's equations, we have to assume something. So let's just assume that Mira is a reasonable description based on ideas of renormalization and various other words. So the way Mira works in this language is you have some local degrees of freedom, you want to remove some entanglement, and then you want to coarse grain or throw away states that have become unentangled with the rest of the system, like this. And then I can continue. I'm only going to draw this picture one time, so it doesn't take forever. Oh, sorry. So you have some picture like this. So I've just shown you a chunk of the network here. And it's self-similar, right? I remove entanglement, then I kind of factor out degrees of freedom, then I remove more entanglement at longer scale and factor out degrees of freedom. And I argued that this network already reproduces much of the geometry, the spatial geometry of this metric, but in a discrete setting. So for example, if you go down to length scale 2a or 4a or NA, where A is the lattice spacing, then you see that distances now become smaller. Right? I can go closer. I can get between 2 points much faster down here because these tensors go very much longer distance. So you can make various concrete statements that, for example, the geometry of this graph with some graph metric on it, just some simple nearest neighbor metric, reproduces sample geodesics of this metric in a nice way. You can also show that the graph Laplacian has the same eigenvalues at low energy, at low eigenvalue as the Laplacian on this space. Right? So there's various things you can do to make this more plausible. Yeah?
How does T come into the picture?
So this is really the state. So T is not obvious here. You can figure out what the metric component GTT is by looking at the renormalization of the Hamiltonian. So if I apply the Hamiltonian up here and then I move it through the network, it'll be renormalized by a certain factor, and that factor can sort of let me figure out that this should be R squared here. But time is not explicit in this construction. I have to sort of infer it from some other information. Yeah.
If you will interpret the mirror as a space-time, then you should break the translation symmetry at some point.
Break the translation symmetry. Sorry, which?
Say at the second level, you have to choose the pair whether
Yes.
it is here or there.
You mean which one whether I do this here or there? Yeah, you have to make a choice. So I mean, but that choice may be an artifact of the network. I mean, what we would want to demand is that this network is approximately or exactly translation invariant. So that will be true for some special choices of these tensors, which you could enforce by rewiring invariance. So you could redo this network in a different way and you get the same answer. So in some cases, we know how to impose that condition exactly to prove the network, even though you make a choice, the network is actually translation invariant. Okay. So what about entanglement? So let me make some definitions. The causal cone, which I write Cc of A, is the set of all these tensors and sites that can influence the state of A. Right? So it's all the degrees of freedom in the network that can influence the state of A. I can also make another definition, which I call the shared causal cone of A and B, which is just the causal cone of A intersected with a causal cone of B. Right, so this is all the things that can affect both A and B. Right. Then it's easy to show from this network that the most amount of entropy that it can add, or the entropy that it adds, is a property of just the shared causal cone of A and its complement. Right, so in other words, all the tensors that connect A to its environment and nothing else. So tensors just within the causal cone of A, but not in the shared causal cone, only affect A without affecting A bar. And similarly, the ones in A bar only affect A bar, so they don't change the entropy. Right? They can change the states within the subregions, but they don't change the entropy. And because this shared causal cone basically looks like this, if this is A, this is A bar, you can think of the shared causal cone as being essentially this surface, roughly speaking. So this is how you can, in words, say that the entropy is just a property of this curve in the bulk. Right? And indeed, you can say that you can basically bound this. I call this A tilde. You can bound the entropy of rho A, roughly speaking, by the size of A tilde times log chi, where these tensors have legs of size chi, which you can think of as being this 2 to the n. Right. And so in fact, we can argue that when this n is large, you would expect this bound to be saturated and that the entropy becomes non-fluctuating and semi-classical, the entropy added by the network. So this is the so-called large n limit. One can argue the bound is saturated. And we interpret this as some kind of semi-classical geometry, non-fluctuating geometry. Right now, it's really just a graph geometry at this point. I'm not going to do anything more than that, really. I don't have time. But anyways, it looks non-fluctuating in a certain precise sense when I have many local degrees of freedom.
Why exactly?
Well, basically what I imagine is that these tensors are kind of quasi-random, so that they just always add a large amount of entropy, independent of what states I put into them. Unless, if I put product states in, let's say, right, which is what I'm doing here. I take something here and I put a product state and then I entangle them. So for product states, a random unitary is going to entangle them a lot, irrespective of what product state I put in. So there's some argument about these being generic tensors. So this looks sort of like the first term of star, right? My fundamental assumption, where I said the entropy is going to be some kind of area term plus bulk entanglement between the degrees of freedom in here and in here. So I've at least, I hope, made the first part of star plausible. Or let me write star up here again. So this term is sort of what we got here. Okay, now, but what about the bulk degrees of freedom, right? So here's the bounded degrees of freedom, and here are the bulk degrees of freedom, where in some sense I put them all into product states, right? But I don't have to do that. This is a unitary transformation. I could put them into other states, right? So to get this second term...
So if you say, if you put this bulk one all to 0, you don't have second term then.
Yes.
I see.
So, okay, there's a subtlety here which I don't actually understand yet, which there's a sense in which maybe the second term is already contained in this formula a little bit, like the vacuum fluctuations are already in here, and this describes the additional entanglement on top of the vacuum fluctuations. But I don't understand this fully yet, so let me not say it. Okay, so to do this, I want to define one more thing, which is the reduced causal cone of A relative to B, which is the causal cone of A minus all the things that are in the shared causal cone of A and B. Right? So this is all the things that really only impact A and can't affect B or anything else. Right? And so you can show that if I were to take bulk degrees of freedom, that is these zeros, and change them to something else, right? So now I put, phi here, and phi prime, and so on, right? If I take bulk degrees of freedom in the reduced causal cone of A relative to its complement, and entangle them with bulk degrees of freedom in the complements, the reduced causal cone of the complement relative to A, right? So this is all the stuff that can only affect A and not possibly affect A bar. And this is all the things that can only affect A bar and not possibly affect A. If this is true, then you can write the wave function, the state of A, as a sum. In fact, it's a direct sum of probabilities times some states associated with basically different choices of bulk degrees of freedom. So this is really, it sounds maybe confusing, but it's really a trivial statement which just says that I'm basically taking some product states and I'm applying a unitary strictly within A. So that obviously doesn't change the entanglement. It's like a local, it's LOCC kind of operation, right? It doesn't change the entanglement. So I have a decomposition like this, and then S of rho A is sum over J, Qj, so it's the average of the entropies of these states, right, plus the Shannon entropy of the Q. Yeah.
So we took by the bulk degrees, you meant the...
Yeah, these guys. So just imagine I take one of these guys and change it to phi, and I change another one way over here at the top layer to phi prime, and I entangle them in some way.
So these two are entangled.
Yeah, these two are entangled. And all I'm doing is I'm applying one short depth circuit, and that obviously doesn't change the entanglement between these two things, right? Because they're far away. They're outside of causal contact in this circuit.
So in this example, J would go over the Schmidt coefficients of this entangled state?
Yes. Yes, exactly. So these QJs are really just the Schmidt eigenvectors of the original entangled state of these bulk degrees of freedom. Yeah?
What would it change if you decrease the gravity to a very small value or completely eliminate it? Like, where does it come in?
Well, so for example, this, as I'm doing it here, so what will happen is, for example, this bound may not be saturated. So it's not clear to what extent you have a single classical geometry. And also this separation of bulk degrees of freedom here and the tensors, it has a nice sharp distinction, this large and limit, in the sense that there's sort of like this big classical geometry and these little fluctuations on top of it. But more generally, it's sort of everything's fluctuating equally and it's not clear. So basically some of the things just sort of are not as clearly interpreted. I mean, I can still do the network for the Ising model. There's no problem with that. I can still do this. This result is still true. But the interpretation of it is not as clear. Okay, and so these S rho, A, J are all the same because I'm just acting within the causal cone. It doesn't change the entanglement. So this is like A tilde, and this is like bulk entanglement. And you can see there is something nice about this in the sense that I had to sort of stay away from the edges between A and A bar in the bulk, right? Because when I act on the edge, that's sort of, it's not clear, does that belong to A or to A bar, right? So there's a little bit of non-locality in the bulk. And that's nicely reflected in this formula, and that this formula is only true when I only act within these reduced causal cones. Okay, so the point is ultimately that I've obtained this formula from the mirror network, which includes both some kind of area law entanglement and also some kind of bulk entanglement. And it's an exact formula. There's no approximation. It's just a true statement about this network. But it looks a lot like star. Right? So although I don't have time to really fully justify, and in fact can't fully justify, the equality of these two things, I hope that this at least makes it plausible that this is a reasonable place to start from. If I assume that this network geometry in this limit becomes really smooth, and if I assume that this term here reduces to the area term, which it should in some special case, for some choice of dynamics, it should reduce, and this bulk entanglement is easy to interpret, then it looks like I get a formula like this.
Okay.
Yes?
Why did you want to use the word qubit in the title? I mean,
Just to emphasize the elementariness of the starting point.
so you put n of them together.
Yes.
As the starting point. And could you have done exactly the same with the continuous theory in the first place?
Yeah, I think so. I mean, I need to be more careful about regulation, but yeah, I don't see what the issue is.
And the regulation may end up being equivalent to start theory.
Yes. Yeah, I want to emphasize that what's good about this is that it's completely concrete. It's puttable on a computer, which is quite different from quantum gravity normally. Right? Normally, there's tildes and approximates and roughly Hilbert spaces, and this is really, I mean, some things are obscured by this, like the symmetry of Lorentz invariance, for example, but it's completely concrete, which is nice. Okay. And that's all this qubits was meant to indicate, that it's elementary, it's starting from the bottom, and it's concrete. Okay, part 2. So now we're going to completely switch gears. I won't say another word about tensor networks. I'll just talk about geometry, starting from this formula. Let's draw this, my favorite picture again. A tilde, and sigma. And the S of A in the Cft state is equal to A tilde, the area of A tilde plus the bulk entanglement. Okay, so now I want to start from this, along with the assumption that there is a geometry and so forth, and to show you that Einstein's equations have to hold. Okay, so again, just to remind you, I'm thinking about I have a Cft state, and this is the same as some set of data, which is a metric, some space-time, and some bulk state, like this. And so to get dynamics, this is just an assumption about the way entanglement is encoded in states, right? To get dynamics, I need to consider a variation. Right, so what I'm going to do is I'm going to consider, first of all, a variation of the Cft state. And I'm going to look for various technical reasons at balls. So A is a ball centered at x of radius r. And now I can work in d dimensions. Right, so it don't have to just be one-dimensional. And so what I can look at, and let me just mention at this point that this I'm going to follow at first some nice work by Lashkari, in which Mark van Ramsdonk was also involved, by Faulkner et al. And then old work by Iyer and Wald. And they'll get us part of the way, and then I'll tell you where we have to introduce, well, I'll tell you where this extra term here really gets us all the way. Okay, so let's look at balls, and let's look at delta S B. So the change, the entanglement entropy of the ball under this change of the state. So if I'm very naive, this is just going to be delta rho B log rho B. That's some kind of naive perturbation theory formula. And it looks intractable, except that actually I know what this log rho B is for these balls in a conformal field theory. I know that log rho B has the following amazing form. It's an integral over B of a weighting factor times the 0, component of the CFT stress tensor. That is the energy density of the CFT with this weighting factor. Yeah, integral over the ball. Yeah, so there's a ddx here. Okay, and I won't derive this formula for you, but I will tell you that it's essentially a version of Unruh's statement that accelerated particles experience thermal radiation. And in fact, this formula by itself is already extremely useful. Just forgetting about gravity, just using this formula for CFTs, in particular because topological states are also CFTs in the simplest case. Just trivial CFTs, right? They're topological. So in addition to not caring about the size of the metric, they don't care about the metric at all. So you can apply this to CFT, to topological states as well, and prove the bulk edge correspondence, for example, for any relativistic topological state. The bulk edge correspondence being the statement that the entanglement spectrum has the same universal properties as the physical edge spectrum. So this is a quite useful thing, but it's just for me a stepping stone, which allows me to derive a constraint on the way that entropy changes are related to changes in energy.
R capital is part of the de Sitter matrix.
R capital. R is the radius of the ball, and R sub ADS is the ADS radius, but I won't really use that. Okay, so what we have is what's called the first law, because if this rho had been just a thermal state, then this would be the first law of thermodynamics. This delta S equals delta E. Delta SB equals delta EB, where EB is defined some kind of weird energy like this. So this is the definition of EB. It's some weird weighted energy inside region D. Okay. So this is all CFT. Okay, but what about gravity?
Sorry, what's the difference between this energy and the log?
Oh, I just rewrote it.
Right. So okay.
I just wrote this formula as this is the operator EB, and then I took. I need to do. There you go. So then, if I put a delta rho B, this is the change in the expectation value of.
So minus log of rho B, you look at this as some Hamiltonian.
Yeah, it's a Hamiltonian. It's this energy operator. This way.
Integration is on the boundary.
Yeah.
It's always on the boundary.
This is space. It's a subset of space in the CFT. Yeah, it's the interior of the ball. It's B, the ball.
And you don't
But
have
the
to
B
write
is
the
on the
temperature
boundary.
there?
Sorry?
You don't have to write the temperature?
I put temperature to 1 or to 2 pi. Actually, so there's a 2 pi I missed. Actually, this 2 pi is understandable, but let me not talk about it. You ask me afterwards.
So in general, I can write this for any system that the entropy change is equal to the average value change of the entanglement Hamiltonian.
Yes.
So it's just in this special case, I have.
I know what this entanglement Hamiltonian is. Yeah. So what I like to do is just to calculate the same quantity on the gravity side. And I'm running out of time, so let me try to be brief. The first thing you can look at is delta. Let's see what I wanted to say here. Yeah, so let me first define what I mean by variations. So delta G, I mean that the metric is now this ADS radius over r squared, dr squared minus dt squared plus dx squared plus some little perturbation which just acts in the field theory directions. So this is just a choice of coordinates. I can always put the metric in this form. And then I also have some delta psi bulk. This is the data which is equivalent to delta psi CFT. Right, because I told you they're just exactly equivalent. And so I want to use this CFT relationship to derive a constraint on these two pieces of data.
So G is the metric.
Yeah, G is the metric. Okay. So let me just do it, or show you how it works. So first let me say, okay, there's delta S grav geometrical part, which is delta. This is what I mean by this. It's the gravitational part of the entropy, which is geometrical, which is this A tilde area. Okay, so this variation, you can calculate, it depends on two things. The minimal surface changes and the metric changes. But because the minimal surface was extremal, that variation doesn't matter, right? It's just equal to 0. So this is actually equal to just the change due to the metric. So I can write it as the integral over A tilde of something I'll call chi. Right? It's just some metric change evaluated on the surface A tilde. Now, a remarkable thing is that we can also figure out what this part is here, either using this first law, looking at very small regions, or using the General Holographic Dictionary, which says that delta T mu nu CFT is proportional to H mu nu as r goes to 0. Okay, so this is part of the so-called holographic dictionary, which relates observables on one side to the other, but it can also be derived just from this relationship, but looking at small balls. And this is something that these guys did.
Excuse me.
Yeah.
So that metric change is quantized, or is it?
No, I'm just doing some semi-classical change in the metric in the geometry. Yeah, it's not quantized. In principle, this can include changes in the state of the bulk gravitons. So that's possible, but that's encoded in this part, not in this part. Okay, and so using this, you can figure out that delta EB evaluated gravitationally is actually equal to the integral over A of this same thing, chi. So this is a non-trivial fact, which is really due to Iyer and Wald. And there's a third fact, which is that the derivative of this thing chi, which is actually a form, it's a differential form, can be written in this way. It's minus 2 So let me explain this. This is a killing vector, which means it generates a symmetry of the bulk metric. I can write it down for you in a second. This is the linearized Einstein equation without matter. And this is a volume form. So this really means you take, to get this delta, to get this, it's the gravitational action times delta GAB. So again, I'm not assuming that the equation of motion holds. I'm just saying that this is a true formula for this object chi, which satisfies these two properties. Right.
Gravitational action integral R?
Yeah. So W grav is the famous thing. Where this is the cosmological constant, and that's the Ricci curvature. But now I need one more ingredient, which is the change in this term here. Right? I've gotten this bit of the entropy on the gravity side, and I figured out what delta EB is on the gravity side. But I need to calculate this. And so, in fact, you can show the following. If I look at delta sigma again, the variation here comes from two sources. The minimal, this region sigma could change in the new geometry, and then the state can change. But it turns out you can show that this quantity is also extremized with respect to the change in sigma. So that part drops out. And this is just equal to minus trace delta rho sigma log rho sigma. Okay. But in something which is quite analogous to this formula, for this special case of balls, it turns out that A tilde is a horizon. It has a very special property. In fact, it's what's called the bifurcation surface of a killing horizon. Okay, and because of that, I actually know, for essentially the same reason I can figure out what this entanglement Hamiltonian is, I can also figure out what this bulk entanglement Hamiltonian is. And it's equal to the following thing. It's integral over sigma, the minus sign, like this. But this is the same killing vector here. Let me just tell you what this vector is. It's minus 2 pi over r. Just like this. So there's some formula which you can figure out. Like this. So I'm just taking this time-like component here. Right? And you can see if I put r to 0, I get back this thing that I had over here. So actually this is the time-like component of a conformal killing vector on the boundary, and it's the asymptotic value of this killing vector in the bulk. Okay, but this formula is crucial because everything is exactly the same as what appears up here. So now the final argument goes like this. I know that 0 must equal delta SB minus delta EB. This is equal to integral over A tilde of chi minus integral over A of chi plus integral over sigma of this particular quantity. So this is the geometrical part of the change in entropy. This is the energy, the change in delta E. And this is the bulk state part. But now I use this nice fact that d chi can be written in this way. say this is equal to an integral over sigma, right? This is a tilde sigma. So what I have here is a complete integral around the boundary. So I can change it into an integral over d chi, which is minus 2 C0 this should be delta change in the, like this. And this is true for all BXR. Right. It's true for all balls. And so you can use this to show that the integrand vanishes. But the integrand is the linearized Einstein equation coupled to matter. Okay. Ta-da. And in particular, you have the equivalence principle, which says that all matter, all bulk matter and energy coupled to the bulk metric universally via its stress tensor and nothing else. Right? So the equivalence principle comes out of this assumption that all that matters is the total entanglement entropy of the bulk fields. That's actually equivalent to the equivalence principle. And now from here, you can do various things. Here I only got 0, 0. You can also get the field theory directions by boosting. So you can get mu nu from boosting. And then mu r and rr are constraints, which express the fact that the CFT stress tensor is traceless and conserved. Okay. So I get all the components of the linearized equations. And in fact, then there's a simple, well-known argument that lets you go from the linearized equations to the nonlinear equations, which says that now I have matter and gravitational fields interacting. They can exchange energy. In order to have a global conserved energy in the bulk, I have to include some interactions. I have to continue dressing things up. And in fact, you can get, in a way which I won't specify, you can get actually to the nonlinear equation by imposing bulk energy conservation, or covariance, if you like. But let's just say from here I got the linearized equation.
So the nonlinear equation would be Einstein equation.
Yes, it would be Einstein's equation
matter.
with matter, universally coupled. So what have I done? I sort of started in the middle with this formula here. And then I tried to argue that this formula is plausible from a tensor network point of view for CFTs. And then I used this formula to rigorously show that if this formula is true, then the linearized Einstein equations hold. Okay. So hopefully I convinced you that there is some kind of plausible trajectory starting from microscopic degrees of freedom in a perfectly well-defined system to get all the way at the end of the day to semi-classical Einstein equations in an emergent holographic bulk. Right. And so with that, let me say thank you.
Thanks a lot. Questions? Yes.
But, I mean, you kind of impose this CFT method. Of course, by itself, it solves Einstein equation. But then
Yes.
you got Einstein equation for what? I mean, for H?
Yes. The linearized equation for H. So the ADS metric follows from symmetry. So I don't need to solve an equation to get it.
But then you're telling me that you can add more stuff and turn this equation to nonlinear
Yes.
for some generalized H.
Yes.
Okay.
Yeah.
So it looks like the gravity is live on the boundary, the matter live in the bulk. So actually this actual degree freedom of 5 prime looks like additional degree freedom you put in the bulk. I don't know whether you...
No, the gravity lives in the bulk too. But the gravity is one of these phi's actually. The graviton is one of this is one of these states you can put in there.
I see. So you say both the matter and the graviton are bulk degree freedom.
Yes.
And the boundary CFT just gave you this background, the ADS CFT bar.
Well, so the ground state of the CFT is indeed related to this ADS.
ADS, I see. Give you this background
But
ADS.
so there'll always be some asymptotic ADS part which doesn't fluctuate.
I see.
That's the sense in which you have in any quantum gravity theory you have some matter conditions you specify which are non-fluctuating. But in the bulk everything is kind of varying, right?
So this is different from the ADS CFT correspondent because there it looks like all the degree freedom on the boundary. But
No,
here you have independent degree freedom in the bulk.
They're not independent, right? at some very basic level in the mirror, all the bulk degrees of freedom, there's just exactly chi to the L of them, where L is the length of the chain. And the mirror is just a unitary transformation which goes from those chi to the L distributed in various ways in the bulk to these L degrees of freedom at the top. They're exactly equivalent. Which is what should be true. I mean, they should just be different representations of exactly the same Hilbert space.
I see. So this 5 degree freedom actually is a boundary degree freedom.
They're not different. It's just a question of how I view them.
I agree with that. The reason is following. Either you use boundary degree freedom only, or you use a bulk, 5 prime only, not together.
Yeah, I don't think I ever used them together.
So you didn't use them together. I see. But from this integration looks like there's a tilde A. Looks like you use them separately.
Oh, well, no, this is still the gravitational stuff. It's just the asymptotic value of it.
I see. So the A part is really not on the boundary. It's still kind of in the bulk.
Yeah, you can think of it as a limit to
I
the
see.
approach, yeah.
So for a generic,
I see.
for a generic CFT, we know the bulk field is not transparent gravity.
Yes.
For example, it can contain many other fields.
Yes.
So I guess all these fields should contribute to this entanglement and actually change.
They certainly do, yeah. But there's another possibility, which is that this formula is not. I mean, it doesn't have to have. It doesn't have to be the area. It could be, for example, the integral of over that area of curvatures. Right. So they're in high derivative gravity. Then this formula is not the right one. You should replace this with what's called the wall of entropy. And then from that, you can actually repeat the whole argument and derive high derivative gravity coupled to matter by positing a different kind of term here.
You mean you get the Einstein because you start from the dynamics?
Yes, because I start from area, which is the simplest in some kind of derivative expansion. But you can consider more general things.
Several years ago, Verlinde wrote a paper which was called Entropic Gravity. He started with Bekenstein formula for entropy and somehow managed to derive Einstein equation. Is this somewhat related?
It's similar, but it's very close in spirit to a very famous paper of Jacobson, where he says that Einstein's equations follow from imposing some kind of thermodynamic-like equation at every point in local Riemann horizon. So here what I'm doing is like that, but only for global horizons. And so I have to do a little bit, you get something different than what he got, but it's similar in spirit to that argument.
Okay, so if there are no urgent questions, maybe we thank Brian again. And